So this is a continuation of the last video that we just showed. The last video was 11D, and now we're going to continue it in 11E. And so what we did is we were talking about circular lenses and their concave lenses, and basically we said that, you know, it's a circular lens, so it's a little bit like this, and we have an optical axis which goes right through the center of the curvature. We have the center of the lens. We have the focus of the lens, which is 1/2 of the distance. It's 1/2 of the radius of curvature. And we talked about the light in parallel to the optical axis goes out through the focus. Light through the focus goes out parallel to the optical axis. And then we just looked at the light coming into the center of the lens is going to go, and I've already sort of marked that out in the previous when I ran out of time, and it's going to come and it's going to go like so. And so all of these rays of light started off at this guy's little headlamp, and they went in 3 different directions, and they all came back to this point. Now, they actually didn't go in 3 different directions. They went in an infinite number of directions, and basically all of the rays of light that sort of hit this region of the lens all bounced in such a way that they all ended up there. Now, if this guy had a little light on his belly, all those rays of light on his belly would all kind of end up there. And so if we put the whole kit and caboodle together, what we would find is we'd find that we had an upside down image we would have our object, which is our little person wearing a couple of lights on him, and we would have, back here, we would have an image of that person. Okay, now we can also do this with equations. So the equation that we can use is 1 over I plus 1 over O equals 1 over F. And so I is the distance from mirror to image. O is the distance from mirror to object, and F is the distance from mirror to focus. So now for my situation, I said that the distance to the focus was 5 3/4. So from example, F is 5.75 centimeters. And my object was located at, that's 11, 12, 13. My object was located at 13 centimeters. And so I'm going to take this and I'm going to rearrange it, and I'm going to say 1 over I is equal to 1 over F minus 1 over O. So I'm going to say 1 over I is equal to 1 over 5.75 centimeters minus 1 over 13 centimeters And so I'm going to say 1 over I. Well, hang on, I'm going to do that on my calculator. So I crank that out. Okay. So I get 1 divided by 5.75 minus 1 divided by 13, and I get I equals 0.97, or 0.097. Okay? That's wrong. Wrong. This is something people do all the time. I'm showing it to you because it's something people do all the time. 1 over I is equal to 0.097. 1 over I. So the units on that is 1 over centimeters. So that means that I is equal to 1 divided by 0.097. So my I is going to be the reciprocal of that, is going to be 10.3. Okay, so then if I look, I have, let's see, that was 11, so I should be actually at 10.3, so hang on a second. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm at like 9.5. So I'm off for some reason. I'm off by quite a bit. But that's okay. I'm not so concerned about it. Okay. So this is looking at the actual curvature. And so what we're going to do in the next examples is we're going to sort of simplify it. So I want to go to okay, ray tracing simplified. We have an optical axis, and we have a curved mirror. I'm going to put it over here. Okay, and this is my optical axis. And then somewhere out here we're just going to say we have a focus right there. Okay, so we've made some dramatic simplifications so that we can draw things a lot easier and so that the diagrams come out better. And the simplification is that rather than drawing the curved mirror as an actual curved mirror, we just drew it as a straight line that says curved mirror on it, and then our optical axis just comes perpendicular to that, and some distance out we have our focus. Okay, so then in the next, now I'm going to do some simplified ray tracing in the next videos.